Hi everyone, it's Peps here. Welcome to another Houdini training. In this new project, we will create this ice cream commercial in Houdini completely from scratch, and it will be divided into 4 separated videos. And in the first one, we are going to create the stick geometry, fracture, and animation. So, starting from an Houdini empty scene, first thing first, let's create our project. So, File, New Project. I will choose the path to save my project and give it a name. Let's call it Ice Cream Tooth and press Accept. Now, let's save the scene. We want to save it in the job variable, so our current project, which is ice cream. And let's call it Ice Cream 01. So we're ready to start. Let's drop down a geometry node. We will call this stick, and this will hold everything about our stick mesh and animation. So dive inside, and we want to drop down a curve node. We will draw only 1/4 of the stick and then mirror it. So we want to go in the front view with the space and 3, and let's draw our stick. If you have the curve node selected and you have the active manipulator, you will see here all the tips to use the curve tool, and with F and G we can swap between the draw and the edit mode. So first we want to go in the draw mode with the NARMS curve, and let's draw some points to define our stick. So something like this. And when you're done with the point, we want to right click and say finish at the point. So now we press F and we go into edit mode and we can adjust these points. So let's adjust it a little bit. And to make sure that we will fuse the point when we will mirror it, let's activate the grid snapping and draw this point here on the 0x and this one here, so we make sure that it's on the 0y. So now to create the surface of a quarter of the stick, we want to merge this curve and this curve transformed with 0 scale on the x. So we set it like this, and if we merge the two curves, we basically have the outline of the surface. So now we can use a skin node. This will create the surface just with the default setting. So now we can drop down a mirror node one time for the X, and we can duplicate it. And on the second one, we want to set the direction to 0 on the X and 1 on the Y. So now we have the surface. If you press Shift and W, you will see the wireframe, and this is still a NURBS surface. So first, let's drop down a convert node, so we can convert this to polygon, and we want to change the setting to division per span, and let's say something like this. We still want something low poly. Now, if you enable the point number, you will see that we still haven't fused the points. So let's drop down a fuse node, and this will fix our surface. Finally, let's drop down a subdivide so we can have something more high poly, and let's set the depth to 2. Let's hide the point number. So now we have our starting surface. So now let's add some thickness to it. We want to use a poly extrude node, let's say of 0.5 for the distance, and of course we want the back also, so enable the output back. And now if we go in the top view, you can see that our stick is no more centered on the z-axis. So let's drop down a transform node, and we want to set it back on the z with the half of the value of the distance. So right click on the distance, copy parameter, and paste relative reference with right click on the z axis of the transform. And we need to divide it by 2. So now our stick is centered on the z-axis again. Now, before the beveling, we want to address the UV part, because for the stick, we want the logo projected on the stick, so we need some UV. And here's a little disclaimer, because I really wanted to use Copernicus for the texturing part, but in my opinion it's way too unstable at the moment, so we will make the texture in Substance, meaning that I really don't care about where my seams they are going to be, because I will make some ad hoc texture. So first we want to drop down a UV flatten node, and as soon as you enable the handle manipulator, you will see that you have the tool option, like the curve node. So you want to shift and click on the edge we want to cut. So let's select one of these, and with A, you can select the range with the left click, or the full loop with the middle click. So let's select one edge and then the full loop, and do the same on the other side. And as you can see here, the island are updating live, but they are overlapping each other. So we want to turn off the enable manual layout. And as I said, I don't care about the seams, so I want to split also here, because I want to end up with the least amount of UV space wasted. So let's split all this loop here, and also on the back and on the side. And I believe we also want to split on the top here and on the bottom here. So now we do have something like that. And I ended up using also a UV layout, so the next step isn't really necessary, but I just want to show you that you actually can align the island based on the global spaces, because as you can see now, if we go out and see the texture, on the UV they are basically rotated compared to the y-axis. And we can fix this with this option where it says axis align vertex group. We can basically define the group to anchor, let's say, that vertex set to an axis. So we want to add a group, and we want to click on the group selector. So we can go on the UV space with space and 5. And now if we grab, let's say, this set of vertex and press enter, the vertex we selected will be aligned to the U or the V axis. And we want to use the U, which is the X on the UV space, basically. As you can see, the island has been aligned, and we want to do the same for the other three pieces here, and also for the side pieces here. So let's add the group and the vertex selection. Let's grab the second one. Let's make another 2 for 1 and 2. And now other for group for the side parts. So 1, 2, 3, and 4. Let's zoom a little bit so we can grab it. 1, 2, 3, and 4. And as I said before, let's compact this a little bit. I ended up using a UV layout, so let's drop down one UV layout, and here we want to re-enable the texture so we can see it. And we want to say axis alignment by island position in 3D, and we want to allow the rotation by 90 degrees step. So we should end up with very little amount of UV space go to waste. It will also say it here. You can see coverage 76.73%, which is not bad. So now we want to define the bevel group. So let's drop down a group node. Let's set it to edge. We will call this bev. And we want to disable the base group and enable the include by edge, so we can define the minimum and maximum angle. So let's make it 95 and 85. And yeah, it seems correct. So now we want to drop down a polybevel node, and we want to assign to the bev group. So now we can apply some bevel to it. Let's say of 0.02 and with 3 division, something like this. And finally, we want to drop down another subdivide so we can have our high poly mesh. Let's give it 2 levels of depth. And let's see if some cleanup is due, but I don't think so. So we can just drop down a normal node and a null. So this will be the out of our stick geometry. So out stick geo, and let's make it green. So now that we have the stick geometry, we want to handle the fracturing part. So let's take an object merge and point it to the stick geometry. Let's move it up here so we have some room to work. And we want to fracture it with some custom fracture made with some Boolean. The RBD material fracturing node does have some good preset to fracture wood, but we want to handle this fracturing completely custom. So let's take a null. Going from the stick geometry, we want to right click on it and make where it is, collapse to subnet, this one, or press Shift and C. So in here we will handle the fracturing, so let's call it fracture geo and dive inside. And we will generate the cutting plane from scratch. I imported the stick geometry just so we can have a reference here while we're creating the plane. So we want to start from a line, so let's take a line and this will be the output. The reference geometry, we want to take it only as template so we can see where it is. And on the line, let's make it 20 units long and give it something like 50 points. We can leave the origin at 0 because we will mirror it. So now we want to copy and transform this line a bunch of times. Let's say 30, and we can start to increase the translate text so we have our cutting planes. Now, in reality, the cutting plane should be straight because this is basically cut from a piece of wood. But I want to basically bend each plane the more we go over the outside because I believe it has a nicer effect. And for this, we need a for each loop. And that's because if we take a bend on all the copies, even if we set it right, which is capture direction on the positive y, the capture length will be 20, and if we visualize the tool, we should be able to bend the lines, but they all bend the same amount. So basically we want to activate the scale by attribute and create an attribute different for each line. And now that I think of, maybe it actually can be done without a loop, but I already did it with a loop, so we will use a loop. So let's take a for each primitive because we want to iterate on each line, and the bend will go inside. So basically here we will have a max angle, let's say 20, and we will bend the copies starting from 0, which is the one in the middle, and going increasing until the last one will reach the maximum angle. So let's take a point wrangle to compute this bend attribute. Now, in theory, this could be a primitive attribute because all the points on each line will have the same amount of bending, but this option right here to scale by attribute requires for some reason a point attribute, so we are using a point wrangle. And for this reason, it would be not so convenient to use this copy number attribute to get the ID of each copy because we should get that attribute on the points with some vex function or by promoting the attribute before the wrangle. For this reason, we just want to use a meta import node. So we can feed this one in the wrangle, and now, as you remember from my other tutorials, we have this detail attribute coming from the first input. So in here, first let's get the iteration number and the total amount of iterations. So let's create an integer variable called iter for the iteration number, and we will use the detail function from the first input. The attribute is called iteration, and the index is 0. Same for iteration number, let's call it n iter, detail 1 n iterations, or maybe it was a num iteration, I believe, then 0, let's see, num iteration, yes. So now we can create this bend attribute, so f at bend, and we will fit the iteration value between 0 and the amount of iteration, and we will output from 0 to a float channel, so chf, let's call it max bend. Close everything and semicolon. Click here, so we create this pair parameter, and let me increase this size so it should be readable. And let's set something like minus 24. So now if we go at the end of the loop, and in here we activate the scale by attribute, we call the attribute bend, and I believe we need to set this to 1 because we define the maximum bending, and it's not working. Let's see why. So we have the bend. I believe the error is in the value. Let's check the final. Minus 12, 24. Oh, we miss an S here. So now should go from 0 to minus 24. Yeah, it's working. So let's template the stick geometry, and I just want to make sure to get the full size. So let's set it to something like this. So let's say, yeah, this should be fine. So now, always inside the loop, let's take a mirror so we can mirror the curve on the y-axis. So 0 on the x and minus 1 on the y. Now let's take a fuse, so we will merge the point on the origin, but we still have 2 polygons for each curve, we just want 1, so let's take a join. And this will merge the polygon back to 1. Finally, we want to use a polyframe to compute an up vector that we will need later. So append the polyframe. We don't need this normal. We want this tangent name, but we want to call it up. So basically, if we create the visualizer for this up vector, we do have this vector pointing along the curve. And that's it for the loop. So let's rearrange things. And here we can template the geometry and hide the up visualizer. So now we have 1/2. Let's create a mirror, and this will mirror on the x-axis, so it is good as it is, but we don't want to duplicate the first curve, because now on the origin we have an overlapping curve, so we should say the group will be everything except the first primitive. So basically, if we don't say keep original and we go in on the front, you will see that we miss the first curve because it's on the original. Now let's take a poly extrude node, and we want to extrude all these curves. Let's activate the transform extruded front, and let's move it on the global z-axis, something like 10 unit. Also take a transform node, because now it is offsetted. We want back on the origin, so let's take the value from the translation on the extrude, copy parameter, paste relative reference on the z, and let's set it to negative and divided by 2. So back on the origin. So now we want to add some noise to this cutting plane. We don't want straight cuts, but we need more resolution, at least on the y-axis, I mean z-axis. So in the poly extrude, let's put something like 25 divisions, so we have some polygons. Then lay down a normal node, and go back on the mirror and say don't change the surface, so they are all oriented the same way. Then make some space, and we want to apply some noise to it, so let's create a point bob, plug the normal, and go inside. In here we will use a couple of noises to create the distortion on the surface, so let's take one turbulent noise. Let's plug the position in the position, and we don't want to add this noise to the position because otherwise it won't follow the normal of the original curve. So we actually want to displace along the normal. So the position goes into the position and the output noise will go into the amount. We also need to plug the normal, and the disp out will go in the position. And as you can see, we are applying some noise. Let's see for the setting, maybe lower the frequency on this one. We want something with a lower frequency first. And maybe we can decrease also the amplitude. Let's put it to 0.8 and decrease the roughness. Set it something 0.25. Now we want to layer down another noise, so let's duplicate this one. We want to add this noise to the other one, and this will be the input for the amount. Now let's unplug the first one for a second, and as you can see, this noise is applied globally on all the planes. For this second noise, we want to apply some diversification to each plane. So similarly for the loop, we want some attribute index for each plane different. So let's go back and lay down a connectivity node before the normal. So here we can call this attribute copy. And on the geometry spreadsheet, you can see that we have this copy attribute going from 0 to 58. So now back in the point bob, we can take this attribute with a bind node. The attribute was called copy and it was an integer. And we can feed this attribute into a random number generator. So random. This will output a value between 0 and 1. So let's multiply it by constant and let's multiply it by 100. So we have some very different values, and we want to plug this in the offset. So now if we increase the frequency of the second one, we don't see anything. Let's see why. The copies here on the points, which is an integer attribute. This is on the points. Why I'm not reading the attribute? Let's take a bind export so we can check. Let's call this one test, and it's working. 0, 1. This should be 0 to 100. Why it's not working? Amount, position. Oh, it is working. Maybe something was bugged in the viewport. Anyway, let's put back the frequency to something like 0.4 on this one and reset also these other two parameters. And as you can see, it's different for each plane now. Also, let's lower the amplitude to 0.6 and maybe the roughness a little bit. So now when we add the two noises together, we should have something more complicated, which is always good. So the output normal shouldn't be needed, but let's plug this also, and let's see. Oh, we should set both of the noises to original Perlin noise. We don't want the alligator because it's going from 0 to 1. The original Perlin noise is centered on the 0, so that's what we want. And that's it for the cutting planes. So we do have the geometry, and we do have the cutting plane. We do have the cutting planes on the output, of course, here. So we are ready to cut the stick. So we want to take a Boolean fracture node. We plug the geometry on the left and the fracture plane, the cutting plane on the right. Let him think for a few seconds, and we do have the geometry cut. If we take an exploded view, we can check what's going on. And it seems everything is working correctly, but we have basically only cutting the stick on the x-axis, meaning we have only one pieces on the depth, let's say, of the stick. So I will say let's add some cutting planes also in the z-axis. So we want to go back in the fracture subnetwork and let's see, after the transform, before the connectivity, we want to merge the incoming planes with another set of planes. So let's take another grid, go on the merge, and let's set this other grid to, let's say, 20 by 40 on the XY plane, so it will cut in this direction, and let's give it a good amount of subdivision. Then we want to copy and transform also this one, so we have a couple of cutting planes. So right now it's on the 0. Let's set it to something like 0.15 with 3 copies. And on the grid, let's put it back on the negative 0.15, so it's back on the center. We have one copy on the center and then other two. And this should be fine for the sides of our stick, I guess. Yes. And that's it. Basically the noise is working. It should work also on this one. Yes. So refactor the geometry, let him think. And now we have also pieces on the depth of the stick. But when will be the time of animation, I want the stick pieces to go following the up vector that we calculated, that we now have lost with the fracturing. So we want to go back inside the subnetwork, and here after the mirror, after the loop, we want to branch out first with a creep node, because if we examine the up vector, you can see that everything is going up. We want the top pieces to go on the y-axis positive and the bottom pieces to be on the other direction. So first we want to clip this geometry on the y-axis, so 1, and then we want to mirror it again, so it will mirror also the up vector on the negative y. As you can see, compared to before, we have the correct up vector. And we need this out of the subnetwork, so we need another output, which is basically the node that is being created when you create a subnet for the first time. You can have as many output as you want. This one, as you can see, has the output index number 1, meaning is coming out from here. And of course it's calculating the fracture again. So now we can transfer with an attribute transfer this up vector from the Boolean, and the up vector is coming from the second input of the fracture subnetwork, and it's on the point, so we can uncheck the primitive, and the attribute is the up vector. As you can see, here we didn't have it, and here we do have it. So we are also good for the animation. Let's disable the visualizer, and as you can see, we have a UV problem on the newly generated group, the inside one. So let's lay down a UV unwrap node. And the inside is already coming from the Boolean. As you can see, the interior group is already here, and it should be here, something like 86k of polygon. So let's plug this in the unwrap node, and we don't want to unwrap everything, we just want to unwrap the inside group. And if we check the UV width, space, and 5, we can see that there are here, they are just way too small, so let's decrease the spacing all the way to 0. We just need the islands to be laid down on a plane. So we want something like this. So in the exploded view, you can see that we fixed the UV problem. And now we want to pack the whole thing. So let's lay down a pack node, and this should be packed by the name of the piece. And the name also is being created by the Boolean fracture. If we go on the geometry spreadsheet, at primitive level, we have the name attribute for each pieces. And as you can see, we have almost 4,000 pieces. So here on the pack, we want to activate the name attribute. And as you can see, we have the correct amount of pieces. So now we can cache this geometry out. We want to drop down a file cache node. Let's call it stick fracture. And I want to use explicit. It's not time dependent, it's just one frame. And I want to write in my job folder, which is the current project, inside the geo folder, and let's call it with the node name, so $os.bgeo.sc. Let's middle click to verify the path, and it seems correct. But before caching out, we actually want to do a couple of things. The first is to define some new normal, because now the geometry is basically represented by a single point for each pieces. So also on the pack, we need to transfer some attribute that we are losing now. As you can see, we only have the position. So we want to transfer the name attribute, the up vector we created, and also the UV coordinates. And after it, we want to use a point wrangle so we can compute some new normal for the animation. And this new normal will go on the point that will animate. So let's define a new normal, and this can be just on the z-axis. So set 0, 0, 1. So basically, if we take an add node and let's say delete all geometry but keep points, you can see that we have the normal pointing on the z. And we still have the up vector also. And finally, we want to promote the name attribute, because right now it's at primitive level. We want to promote this on the points. So let's plug this attribute promote. The original name is name, and it's from the primitive to the points. And as you can see, we have the name attribute on the points now. So let's plug the file cache and save our geometry. So we have all we need to animate the stick, and let's make some order up here. And the way we are going to animate the stick is by basically acting only on the points, and then we will link back each piece to the correct point. To do this, we are going to use a node called transform pieces, which, as you can see, it takes 3 inputs. The first input is the piece geometry, so it will feed the output of the file cache. Then we need the animated point, let's say, and to get the points, we are going to use an add node after the file cache and delete geometry but keep the points. This is the node we used before to test the normal vector. This will go into the second input. And as you can see, it's kind of working, but there's something wrong. And this is because we need also the third input for the rest point, meaning the position before the animation. So we will feed the add node also in the third input. And what we're going to do is to create the animation here on the second, basically the second chain. So if we take, let's say, a transform node, where is the transform node? And we scale only the second input, which is the animated point, you can see that we have a correct behavior. So all we need to do now is to actually create the animation. So let's delete this transform. We will apply some scaling, but not with a transform node. And maybe let's rearrange things to make some room. And if you press Alt and drag, click and drag on a chain, you will create this reroute node, which are very handy. So first thing first, let's take a twist node, which, by the way, if you take a bend, a twist, or a taper, as many nodes in Houdini, you realize that they are the same node, they are just presetted in certain way. So doesn't matter if you take one of those, it's always the same node. So first we want to twist these points a little bit. So we want to twist it on the y-axis, so 1 and 0 here on the capture direction, and the length will be, I believe it was something like 12, yes, and we want to activate the deform in both direction. So now if we twist the mesh, we can say something like 380, so we will have something like this. Now, we will apply other transformation and deformation to the points, but before doing that, let's create the animation, because right now everything is twisting the same amount and it's not animated. What we want to do is basically to create an animated attribute that we'll use to scale all the deformation, and this attribute will be at the let's say maximum value at the start, so the stick will be completely shattered and deformed, and then we will decrease to 0, so we will have the original points. To do that, we will use a point VOP, so let's take it 1, and we will apply the point VOP before all the deformation, of course, so we will have the attribute, and let's call it calc deform, and dive inside. Now, as we said at the start of the animation, the pieces will be all scattered, and we want the, let's say, construction effect to start from the center of the stick, spreading to the borders. So we need to take in account the position. And since we want this to be acting both in the positive and in the negative axis, we want the absolute position. So let's take an absolute node and plug the position. So basically, if we take a bind export and we create the attribute we want, let's call it deform, and it will be a float type. Let's plug the output of the absolute, and if we go outside and create the visualizer for this deform attribute, you can see that now we have something, but this is outputting a vector attribute. We just want the y value. So either we use this vector to float, so we can take the whole vector and take only the second component, or we can use this get vector component, which is basically doing the same thing. You just need to specify which component you want, in this case the y-axis. And of course now the visualizer is outputting the whole range, going from 0 to this should be something 12, but we are seeing only the 0 to 1 range, so we need a fit node, and after the vector component we want this source max to be basically driven by some parameter that we are going to control. So for the moment, let's say we set the source max to something like 14, so we are sure we are including the whole range. And right now the deform attribute, of course, is outputting from 0 to 1, as you can see, because the fit node by default, the destination max is 1. So if we go on the twist and we say scale by attribute, and the attribute is deform. As you can see, it's been scaled by the attribute we just created. Meaning, if we go inside here and we somehow control the source max and the source min, we can create our animation. So let's promote these two parameters, the source min and the source max, by middle click and promote parameter, and double click to expose the promoted parameter here. So we will call this source min, let's say p min, and by default let's leave it as 0, and the source max will be called p range. This is the 14 we decided before, so let's set it to 0 for now. And we don't want to just promote it, but we want to add the min to the maximum, and the result of the add node will be the new source maximum. So what this means is if we go outside and just display the calc deform, let's set the p range baked to 14. So what's happening now is that basically the new maximum of the animation is the minimum plus the range. So when we are increasing just the minimum, we are actually shifting the whole ramp, let's say. So basically we want to start from some negative value, let's say something like -3, and let's put a keyframe on this. And let's say also let's set the FPS. In my case I want 25, so apply FPS. And for the sake of the entire course, let's put the end range to something like 800 and apply. So now I believe we shift click and go on the curve editor. Yeah, it's still on frame 1. Sometimes when you switch your FPS value, the keyframe will shift to a not integer value, so always make sure to set your FPS before you set your keyframes. And we want this to last, let's say, 4 seconds. So here we are going to increase the range until it's fully covered. Let's say something like 12. And I also want to shift click again to bring up the curve editor and G to frame my entire curve, because I don't want this ease effect. I want a linear interpolation. So drag and click to select all the keyframe and here choose linear. So basically we should have the animation correctly set up, and if we display the twist and hide the visualizer, you can see that moving forward we have the stick coming to the original position. So now we just want to add more deformation to it. So let's put the display flag on the actual pieces so we can see what's happening. And now we want to apply some scaling because we want the piece to be more scattered on the y-axis. So let's take a point angle after the twist, and here first let's write the deform attribute to a variable. So float deform, we will take the deform attribute, deform and semicolon, and now we want to take the y position, so at p.y, and we want to multiply it by this deform attribute, so multiplied or equal deform. And of course we need to fit this value because right now the deform it will end at 0 during the animation, so right now the position of each piece is 0, so we want to fit this value with fit 0, 1, because we already know that the source minimum and maximum is 0 and 1, and the new value will be between let's say 1 and 4. So now at the start of the animation, the y position is multiplied by 4 and it's really scattered, and then it will come to the original position when it will be multiplied by 1. And if we zoom in, you can see that the actual animation is following the correct up vector and normal, because we are calculated and kept that value. If we basically delete the up vector, before the deformation, so delete up, you can see that the whole animation is messed up. So that's why we compute an up vector and a normal before on the points itself. And now for another deformation, we want to apply a taper after the wrangle, so we can use a different capture setting compared to the twist one. You could apply a taper effect in this node. You can have bend, twist, taper all active in the same node, but you need to use the same capture setting. And we want a different one. So let's go on the linear tape. Even better, let's go on the transport pieces. And in here, let's set the capture direction always in the y-axis, so 1 and 0. Deform in both direction, and the capture length, let's set it to something like 40 for now, and let's see what we have with the taper. So let's start to increase the taper value. We will set it to something like 10. And of course we want to scale by the deform attribute. So deform here, and maybe also some squish value. Let's say 5, scale by attribute, and deform also here. And maybe I want to squish the pivot really low. Let's say I want something like this, and maybe increase the capture length a little bit more. Let's say 47. So now we do have something like this. And actually I don't want a linear interpolation, so back on the calc deform, let's shift and click. I want some ease out effect, so I will select my last keyframe and do something like this. And on this one I want to start linear, so let's say I'm happy with something like this. Let's enable the real-time toggle and play the animation. Yeah, let's say I'm happy with the result. And here's something weird is happening. Maybe I squished the pivot a little too much. It actually doesn't matter so much, because between the motion blur and the camera frame it won't be actually noticeable, and I like the look as it is. What we want to add finally is some rotation on the axis of the piece itself. And to achieve that, what we want to do is basically rotate the point normal by a full 60 degree at the start of the animation, and then decrease that rotation until it reaches 0 at the end. To do that, we are going to use quaternion, because quaternion are a very convenient way to handle rotation, because you don't have to deal with matrices or transformation order. With a quaternion, you can take a vector and say, rotate this vector by a quaternion. Inside the quaternion itself, you just need to define the angle of rotation, so how much do you want to rotate the object, and on which axis. And we have both, because the angle will be a full 360 degree, and the axis we want to rotate on is the up vector. So basically we just need to say to the points, rotate your normal using the up vector as a pivot point by a full 60 degree. So we want to go back in the point wrangle where we define the scale, because we can write the rotation also here. And we are going to use this qrotate function. As you can read, it's a vector function, and it takes a quaternion and a vector to rotate. We said we want to rotate our normal, so we need to define some new normal that will be equal to this qrotate function, qrotate, and the quaternion, let's call it quad, we still haven't created yet, and the vector which we want to rotate is the normal itself, so this kind of thing. Of course we have an error because we don't have the quaternion yet, so if you look for quaternion on the help page, you can see that we have many ways to define quaternion, but we said we want to use this way. which we need an angle and an axis. So let's make some room here and create a quaternion, which, as you can read, is a vector 4. So vector 4, we will call it quat, as we say. It will be equal to the quaternion function, and the angle, we still need to create it, but let's call it angle, and the axis is the up vector, so at up. Now we have an error on the angle, of course, so let's create an angle. It's a float channel, as it says here, so float angle, and we will create a float spare parameter, so chf angle and semicolon. Click here to create the space parameter, and as you can see, something is happening. Now, we said we want a full 360 degrees, so for convenience, edit parameter interface here, and let's look the angle and set it from 0 to 360 degree. Apply and accept. But as you can see, it's not really working. This is because the angle used in the quaternion function, it needs to be expressed in radians, and we are using degrees, so let's convert this angle from degrees to radians. And now from 0 to 360 we have a full rotation. So now we don't want to animate this, we want to multiply this angle for the deform attribute. So before the radians conversion, let's add a multiply by the deform variable. So now let's disable the twist for a second, and let's just take the rotation. And it's not seems to be working for some reason. Let's check. Oh, we actually need to multiply it after the radians conversion. And of course, we need to set the max angle to a full value of 360. And now it's working. So disable the visualizer, let's check the pieces. And everything seems to be fine. And finally, on the points, since we want to use motion blur, it is a good idea to compute the point velocity. So drop down a point velocity node, and here it by default will calculate the velocity from the deformation. So if you go on the geometry spreadsheet, let's filter the V attribute. As you can see, now is computing the velocity. And also let's quickly check the piece geometry. So let's increase this exploded view. Yeah, it would be a good idea to fix these weird normals on the inside group. So after the cache, we could do it before, but let's do it after. We can unpack the packed geometry. So here we again have all the polygons. So if we plug this to the exploded view, you can see that we have some normal issue on the polygon. So after the unpack, let's drop down a divide. And here we want to say to triangulate only the inside group. So inside, and now we can assign some new normal to the inside group. So here, let's check inside, and this should be fine. So this will go on the first input of the transform pieces. And I believe that's it. We have the stick animation. So let's drop down a null. This will be out stick anim. And also we won't need this fracture geometry after the animation is finished, but we need the geometry for the other cuts. So let's put down a switch node. And This animation will go into the first input. For the second input, let's take an object merge. And it will point to the out stick geo. The animation is 4 seconds long. Maybe let's increase it. That's too fast. So shift click on the animated parameter and let's bring this one to something like 225. And maybe adjust the curve. Let's reframe it so we can have a better view. Whoops. Don't overshoot the curves. So we do have something like this. And here on the switch, we can say that around 200, let's say, we will switch the input. So dollar current frame is greater than 200. So if we highlight the switch, you can see that now it's taking the first input. The dot line is the excluded one. As we passed frame 200, we are switching to the static geometry. And if we middle click on the stick animation, now you can see that we still have the unpacked geometry. Now, for some reason that I quite didn't understand yet, in Karma, unpacked geometry are faster in the viewport, but this is not a good practice. When you're working with transform pieces, you should always work with packed geometry. So after the normal layer, let's repack everything with a pack node and make sure to transfer what we need, which are the normal for the surface and the UV coordinates. So now also we need to specify the name attribute, which is name. We have that 3,800 something pieces. And as I said, unpacked geometry works better in Karma. So here, since we are outputting the final null that will go into Karma, so this will be out stick. We actually want to unpack the geometry again. So unpack on the stick animation, of course. We don't need to unpack this. This is a entire surface. So we have everything back here ready to render. And that's it for this first video. We will handle the texturing after we create the whole geometry. In the next video, we will create everything about the cream geometry, animation, and simulation. So I hope to see you in the next one. Cheers!